Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Today we are joined by Lieutenant Kaitlin Poole, a quantum networking lab manager who works with lasers and communications so small it has its own science.
In 3, 2, 1.
Lieutenant Poole, welcome to the podcast.
Awesome, thank you for having me. I work up at the Information Directorate in Rome, New York. We have multiple quantum groups up there. The one I'm involved with is the quantum networking group, where we are hoping to use trapped ions in combination with photons to build a secure communication network.
So for a lot of our listeners, we kind of talked earlier about how quantum's kind of a nebulous thing for many people. Can you kind of break down what your job is there and what quantum means for us and the security of our nation?
Quantum is essentially the science and the laws of physics behind anything that's really small or basically at the single particle level. So it's when you're working with single atoms, working with single photons, which are particles of light, as well as working with superconductors, because the laws around them, actually, the laws of physics and quantum kind of take over and have more power over what's happening than the classical laws of physics that you learn in your physics classes in high school.
So what's it like kind of breaking into that field? Do you have to relearn the laws of physics almost, or is it just augmenting what we know?
It brings it down to more of a fundamental level. So if you take kind of the statistical average of a lot of the quantum mechanics laws, they become the classical mechanics ones. If you start describing the actions of every single particle, and you have Avogadro's number, so 6 times 10 to the 23, approximately, number of atoms that you're trying to explain, the math gets really, really big. So that's why for systems like how a ball goes through the air, we describe that using classical mechanics. If we're talking about a single particle where it needs to be in a really high vacuum, in my case, I'm familiar with the ion area, and ions are just charged atoms. If we have one in our trap, we can do some really unique things that aren't necessarily possible otherwise.
What are some of the things you've done?
So the fact you can trap a single particle is really cool. The approximate size of that particle is on about 40 nanometers. That's about, if I'm doing my math right, it's about 1,000 times smaller than a human hair.
Oh, wow.
It's tiny.
And for these devices, then, how are you capturing these ions?
So how we capture them is we use a combination of electric fields and lasers to control what we're doing. So we can use electric fields to do the, with some RF input, is to kind of do the physical trapping. And then we can use lasers to kind of keep it in the trap longer, as well as do our state control and run our experiments.
And if you're able to talk about it, can you kind of describe what this apparatus or what kind of the lab scenario looks like where you're working?
Yeah, so I essentially work in a laser lab. We have 4 large optical tables. On average, they're about 4 feet by 8 feet. On one of them, we have 5 different laser systems that we use to control the ion once it's in the trap, as well as to get it into the trap. Because in our vacuum chambers, we start out with a stream of the element we're using, which is a terbium. We start out, and the acronym for that is YB, if you don't want to try and spell it. And we start with a stream of neutral ones. We can use lasers to kick out one of the electrons to make it turn it into an ion.
And what, you said it was a terbium? Mm-hmm. Or why did you choose that element to work with?
It's been studied very well in academia and industry, primarily in academia, as well as it was an ion that we knew we could go from empty optical tables to having the vacuum chambers and the lasers all there within a 2 to 3 year program.
So you trap this ion and then you run tests on it. What are you hoping to accomplish through the test?
Yeah, so with the test we can actually do, some of the things we can do is create a superposition state, which is when it's kind of like that Schrodinger's cat example of it can be in 2 states at once until we decide to look at it, and then it's one or the other.
Sorry, I'm trying to wrap my head around that. So how do you, I guess can you break more into that, kind of what that test looks like?
Yeah, so when we're testing that, we have our ion trapped in our vacuum chambers, which are on a separate table from all of the other lasers. And then we can apply either microwave pulses or optical pulses at the different frequencies to put it into split it between its 2 ground level hyperfine states. That gets kind of really nitty-gritty into the quantum. But if we take the example of like a light switch normally is on or off. In quantum, it's on or off and off until we look at it.
That's fascinating.
And then this is, by itself, it's just kind of a really interesting thing.
Yeah.
But when we put it in combination with this other quantum property called entanglement, then that's where the power behind quantum computing and quantum networking and the security that we get with quantum communication comes in.
Yeah, going deeper into that, so what are a lot of these practical applications, or with entanglement, how can we use this?
Yeah, so entanglement in combination with superposition gives us an exponential scaling of the state space available to us to do computing or to give us how many available answers there are. So then it scales at a 2 to the n rate. So if we have 2 particles, we have 4 different answers. If we have 5 particles, we have 1,000 different answers.
Wow.
And you used the analogy earlier of, was it Schrodinger's cat?
Yeah.
Could you explain that? Because I mean, I heard about it on Big Bang Theory, but you know, maybe that'll help our listeners understand kind of what you mean about these different states.
So Schrodinger's cat is essentially an experiment where they put a radioactive atom or radioactive substance into a switch, and that switch, if the atom decays, then if that switch will get flipped and release a vial of poison. So it's not necessarily a happy experiment, because then you have this apparatus that you put in a box, you put a cat in the box, and then you close the box. And you don't know if that decay has happened, so technically without actually opening the box, the cat is alive and dead until you decide to open the box and figure out what happened.
And it's amazing how that translates to quantum, because again, many people don't know what it entails. So kind of stepping back a little bit, what pulled you into the idea of quantum? Like, what made you want to work in this field?
So when I initially got to Rome about 3 years ago, I had my undergraduate research background with some lasers and materials and optics. And so when I got to Rome, I was like, well, let's try and find myself a laser lab. When I got there, my boss at the time had started introducing me around to different program managers that needed a lieutenant to help with some of the work. And I got in touch with Dr. Kathy-Ann Soderberg, who is one of our program managers up in Rome for our entire quantum effort. And they had a lab that needed lasers set up. So I got in touch with them, and I've been working with them ever since.
And before then, you were interested, you said, more in optical laser work. Did you do any tests outside of quantum with optical lasers?
Yeah.
Or is it really all centered around quantum?
So in my undergrad, I did research with laser spectroscopy of materials that had unique elements in them. So these are called rare earth metals. And so we would try and put those in some of your like standard crystals. So I'd try putting erbium, which is in those 2 lines that get popped out of the periodic table. It's one of the elements in there, into a sodium chloride or a salt crystal.
And just saw how that affected the beam?
To see how it affected properties of the crystal. So if you send laser light through them, the spectroscopy, whether it absorbs or emits the different light, kind of like how your sunglasses will filter the UV light from the sun, we were testing for what wavelengths of light this kind of would absorb over time.
That's really cool.
That was within a physics field?
Yeah, so that was a physics lab that's run by Professor Rufus Cohn up at Montana State University. The other laser research I did was actually with Kirtland Air Force Base. I was able to be a part of the AFRL Scholar Internship program.
Oh, wow.
That's run in conjunction with USRA. And I did that for 2 summers. I worked with the Ultra Short Pulse Laser Lab as part of the Directed Energy Directorate, and got to do stuff with some really powerful lasers. With them being ultra short pulse, they're kind of unique, and you can have really powerful lasers like terawatt class lasers.
Oh, wow.
But even then, because the pulses are so short, so the pulses are on the order of femtoseconds. That's about 10 to the minus 15. To give perspective, about a tens of femtosecond pulse, if you do you know how fast it's going because it goes at the speed of light, and you know how long it is, it's about the width of a human hair. And if you were to do the length calculation.
And that was just work you did through the program then with Kirtland?
Yep,
So,
I did a 9-week and a 12-week internship with them.
Yeah, so and AFRL Scholars isn't just for active duty. I think you had a ROTC background.
Yep, I did RTC through college, but I did this internship kind of independent of all of that. I'd heard about it through a captain that I met through ROTC, but I applied as a normal undergraduate student.
and has a lot of this work then, working with lasers, directed energy, and crystals, kind of helped your work in the quantum field?
Definitely, because I was able to, they could give me the ideas of what each laser needed to do, and what specific optics I would need to have in each kind of setup around the table. And then I was somewhat free rein to design on how the laser goes around the table and eventually into a fiber optic cable to get it to the vacuum chamber where the ions live.
And with what you're doing then, how closely do you work with the teams, like working with entanglement and building a lot of these computer systems?
So we're not necessarily at AFRL, we're not looking to build a quantum computer. That is a very large effort that is probably still a few decades away.
Okay.
In the nearer term, we're looking at, as AFRL as a whole is actually looking at the areas of quantum timing, quantum sensing, quantum communication, networking, and then in the end, we are staying aware of everything going on with quantum computing as well. And in that area, we're looking more into the quantum information processing and specialized processing, not necessarily universal quantum computing.
And how does that work with quantum communications then? Is that something you yourself are working on, or you said kind of the team is developing?
Yeah, so I would say it's a whole team. It's definitely a team effort. Having only my bachelor's, it doesn't necessarily give me enough background. It gave me enough to be able to work on it and kind of do the smaller steps required for the end goal. But for kind of the masterminds behind the experiment, both have their doctorates in the field of ion trapping.
Okay, gotcha. And what does it entail then for communication? Like, what can that look like for us if we use quantum communication?
Yeah, it will bring us kind of ultra secure communication. So thanks to those properties of entanglement and superposition, if we combine those, it can actually provide us a tamper-evident and tamper-proof communication network.
So if you send me a message, right, I have I'm going to use the wrong word, like code, I have the resources to actually figure out what you told me. But if Kenneth, to my left here, if he got it, he wouldn't know what to do with it because it wasn't intended for him, and then you would know that I didn't get the message, so that it maybe was intercepted, sort of thing.
Yeah, so that's one way. Quantum communication is basically if you get my message and something isn't right about it, then you know that it's been tampered with. Because if Kenneth here decided to take the message, somehow recreate it and send it to you, A, there would be a timing delay, but B, there would also be, it wouldn't be this exact same information. Because in quantum mechanics, there's such a thing as a no cloning theorem. So whatever I create, he can't recreate exactly. He can get close, but it won't be exact, and we'll be able to tell that with the results that you get.
So that's the tamper-proof part of what you
And
said.
tamper-evident.
Tamper-evident, okay. Because then we could confirm with each other through a different mechanism, I guess.
Exactly.
To see if it...
And so, as well as during the demonstration you saw yesterday, we're able to create a photon pair source. So we can do entangled photon pairs from a single source. And if you and I trust the source, then once we receive our photons, we can use the properties of quantum teleportation to send the information back and forth. And then it doesn't actually involve any data coming from you to me. It's only from between us and the source.
Quantum teleportation.
Yes.
Yeah, we were trying to get to teleportation today.
Whoa, that's really cool. So
Yeah.
hold on, what is that?
So if two particles are entangled, they are correlated regardless of the distance they are apart. So if we had two quarters that were entangled and I gave you one, then anytime I flip mine, and mine lands on heads, yours will always be heads.
So that's how you could transmit a message. You can say, hey, instantaneously, you have this now.
So it's not faster than light. We don't break the speed of light with this.
But we'd feel like it was.
Yes.
It'd be fast.
It'd be fast, yeah.
It'd be
okay.
fast, but it relies on getting the message from the source of the entangled photons, or me sending a nondescript message that an eavesdropper wouldn't care about of say, hey, look at your system in 5 minutes.
Okay, so in the way this works then, you mentioned that through your lab or through a process, you'd pair these, and then you have to separate them?
Yep, yeah, once we make the pair, we can send them in different directions.
And how do they know they're still paired then?
Based on when we receive the message, because you can do the entanglement in kind of different ways you can do it with polarization, you can do it with time, you can do it with position. And there's different ways to measure them, and so that would mean that we entangle in a certain way.
And you mentioned there's an experiment you have showing this?
So in the photon group, which works in the lab next door to mine, they're more in that quantum computing thrust, more looking in that specialized quantum processing. They've been working on integrated photonic circuits. These are essentially little circuit boards for light. They're about the same size as your computer processor. So they are at that chip scale of like the size of my fingernail. We also recently, through some collaborations and with one of our industry partners, we were able to get a 300 millimeter wafer size of entirely quantum experiments in these integrated photonics. So it has a rectangular pattern that's repeated 64 times within that 300 millimeter wafer, and within that pattern there's 44 different sets of experiments, and then within each of those 44 sets there's around 10 different experiments that we can do.
Yeah, and I saw the wafer yesterday, and the circle is like a little bit bigger if you look like the circumference of a basketball, and you have that many experiments on that like thin slice.
Yep. Yeah, so it's a single layer silicon wafer. It's the same thing that they use to make in CMOS fabrication.
I didn't realize it was so small now. Like we actually had it at such a small scale. Well, literally I know it's a small scale, but didn't know how small the wafers were.
Yeah, so they're one of the leaders as far as getting some of the swap, so size, weight, and power concerns down to a level that we can start thinking about how do we make this robust enough to take it outside. Because traditionally quantum experiments have been done in fairly pristine laboratory environments, because when we're talking about the single particle level, they are also some of the best sensors in the world, and they're literally affected by everything unless we isolate them. So in the case of trapped ions, we isolate them in our vacuum chambers. And so our vacuum chambers are quite large. It's like between we can generally fit 2 of them plus whatever optics to do the readout, take up a whole 4 foot by 8 foot table.
And what would you say, if you can talk on it, is one of the coolest either breakthroughs or discoveries your team has done in the past few years, or at least months you've been working?
Yeah, so in the past few years, we were actually one of the first AFRL labs and potentially first in the DoD to have trapped ions as a capability for the Air Force. We got that capability, and we were successfully trapping back in April of 2017.
Nice. So it has been some time now.
Yeah, we've been making some steady progress to get towards these proof of entanglement experiments. We had some minor equipment things go on, so set our schedule back a little bit, but we're definitely moving forward and making steady progress towards that goal of those fundamental experiments that have been done in industry and been published in Nature and by academia, and get that capability for the Air Force to have in-house so that we can start figuring out how to improve the engineering of these systems so we can put them in, to start potentially put them out of a lab and in maybe a Connex somewhere.
What was that in a what? Somewhere?
Connex, like a shipping container.
Oh, okay.
So that it's still somewhat protected from the environment. We can maybe still put an air conditioning unit in it, but it's not a lab environment.
Yeah, so going closer to the real world application,
Exactly.
I guess, like baby steps.
Mm-hmm.
And for your job title then, what is a normal day for you, or what does it kind of look like in the lab?
Yeah, so a normal day for me is I come into work, and like any of us, I check my email. I also check in with the team to make sure that they don't have anything that I need to do, or if there is things for me to do, I'll start working on them. Some of the things I've been helping with a lot is writing some sole source letters for equipment, because with quantum, a lot of equipment is actually quite specialized. And we really do need certain lasers from one company because we know that they make it at the right wavelength as well as right output power and stability that we need for these experiments. Or for vacuum chamber parts, there's only so many companies that do that.
That's fair, yeah.
So sometimes sole source letters are used when there's only one company that makes the product.
So this is so you have more of a managerial role
Exactly.
to the day-to-day, but
Yep.
for experimentation, you said it's only when they need assistance, or is there certain experiments you're always hands-on?
Generally when they need assistance nowadays, last November I got picked up and selected to start at AFIT here at Wright-Patt this fall.
Oh, very nice. Congratulations.
So I'll be moving here in about a month. So more recently, my day-to-day stuff has been kind of in the lab on an as-needed basis and kind of helping with that background paperwork between some of the maintenance stuff we've needed to get done, as well as just helping where I can. And coming to events like this at the Wright Dialogue or AFRL Inspire, where I can talk about the work and let everyone else that's as smart or smarter than me actually do the work in the lab.
Yeah. And what are you going to be learning at AFIT?
I'm going to be getting my master's with the electrical engineering department and with a focus on high power microwaves. So I'll be changing gears a bit, but it's exciting and it's definitely a field that has some interest to me.
Yeah, did you get any exposure to the high power microwave stuff during your AFRL Scholar?
Not so much in the high power microwave. I got to tour their facility because the program down there, they were able to kind of set up lab tours for the interns. But yeah, as far as microwave, I have some exposure to it because with those high power ultra short pulses, there's some microwave effects that happen because your pulses are so short, or you focus them in air and they make a plasma. So there's some cool effects that happen there. So I have some minimal exposure.
Sure.
But in the end, it's all somewhat in that electricity and magnetism area and electromagnetic waves. So it's just a different frequency range than I'm used to.
I think you're setting yourself up to spend some time in AFRL. You know, we got to directed energy areas and things like that.
Yeah, and I'm excited about that. I'd love to stay technical as long as the Air Force will let me. And being in the physicist career field, I have kind of a unique opportunity versus our engineers and our program managers to do a little bit more time with AFRL.
Fascinating. That's
Yeah,
awesome.
thank you.
So usually we kind of wrap things up. We want to see if you have a message for people looking to have or go around a similar career path that you've taken. And then after we, if you have a special technology or researcher that's really inspired you from the Air Force perspective, you can let us know.
The quantum community is very open to having new people. We will teach you all of the quantum you need to know. You don't need to have a physics background to be a quantum scientist, quantum engineer. We welcome anyone with computer science, with engineering, and all kinds of engineering because a physicist isn't necessarily the best at downsizing things, whereas a mechanical engineer or a systems engineer might be much better at that. And so we're welcome to have anyone. And yeah, we will teach the quantum you need to know, and having motivated people is one of our biggest things.
I think you'd mentioned to me you even have someone with a biology background kind of in the field,
Yep,
which is totally unexpected.
Yeah, we have both an intern and one of our contractors have biology backgrounds, and we'll teach them the quantum they need to know to be able to work on our experiments. One of them I work with more closely, and she helps us a lot with getting our experiment running on a day-to-day basis and maintaining our lasers.
And then the final question we had was there any researchers or technologies that you think are really cool in the Air Force or that have inspired you?
Yeah, so the whole area of quantum is kind of inspiring in a way of we're at that cutting edge of technology that can really help augment as well as eventually help a warfighter. Of if we can have secure communication, then hopefully we can get messages back and forth that we really do want to keep to ourselves. The other thing that one of the end goals of quantum research as a whole is to be able to do standard communication and be able to continue operating in GPS denied environments. And that's where the areas of quantum timing and quantum sensing are kind of the leaders of that area of how do we get atomic clocks and how do we downsize them such that we can put them in planes, put them in cell phones. And there has been some very recent advances from NIST, and they made a chip scale atomic clock that's about the size of a matchbox. It's not quite as accurate as our cesium clocks that we send up into space, but it's pretty darn close.
It's getting there.
And then the sensing, of course, when you're at the single particle level, they're sensitive to everything. And so we can take advantage of that, and hopefully with the Sensors Directorate here at Wright-Patt, there's active research going on in that area. And I just really like that all of the research in this area it's going to help someone someday. And that's kind of one of the big things that drew me to doing research with the Air Force is all of our research has a purpose, and a purpose to help someone.
And it looks like a very bright horizon for quantum in the future. So
Yeah, definitely. And then I would also note that we're not necessarily looking to replace classical systems because we have some very good, like gyroscopes we have some very good ones out there. And with small form factor, or even our like high performance computing is really good. Quantum computing is actually just kind of augment what we can do and be able to do certain processes a lot better. So then we can take the load off and let the classical computers do what they're best at and let the quantum systems do what they're best at.
Yeah, that's a good way to put it.
Yeah, that's a really good wrap up there.
Awesome.
Cool. Thanks for joining us.
Yeah,
thank you so
thanks for
much.
having me.
And to keep up to date with future and past podcasts and to check us out on social media, make sure to see us on Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And make sure to stay curious.
Logging off.